Okay, so this last unit that we have put together is called Advanced Chemical Reactions, and it's kind of a little bit of everything. So today's lecture is going to talk about two different topics. We're going to talk about entropy and reaction rates, and I'm also going to mention catalysts to you. So this thing is meant to go along with your PowerPoint, so you can kind of follow along with that as you're watching this video. First topic that you'll see is something called entropy. Now, the thing with entropy that gets kind of confusing is, first of all, it's abbreviated with an S. Don't ask me. I know it's one of those things, but energy is already an E, N is already used for moles, temperature is already used, R is already used. We kind of ran out of letters, so entropy is an S. It sounds very similar to another word you guys learned earlier, which is called enthalpy. That was the H. But they are two very different things, even though the words look alike. So we're going to get rid of this enthalpy word, and we're going to focus on the entropy. What entropy is, and again, you can see this in your PowerPoint, it's the measure of disorder or randomness in a system. Now, that's a really hard thing to kind of visualize, but it's really how random are the particles? How organized are they? Or better yet, how organized aren't they? So think about it this way. If I have two different boxes, just like this, and I put 5 particles right here, okay, that is not a very random distribution. Everything is even and perfect and spread out, exactly even distribution. Whereas, if I come over here and I put my 5 particles kind of like this, that is a non-uniform, that's a very random distribution. Believe it or not, there is a natural tendency for systems to move towards this. We actually see that systems tend to have an increase in entropy. Things don't stay neat and tidy and organized as much as we may like them to. So the example I have in your notes is diffusion. If we have a little spray bottle here, some kind of aerosol can, and we spray something out, when it first comes out, every little particle is right smack in a little line with the nozzle. Everything is very, very, very organized and non-random. That is a very low entropy. Whereas, after I let this thing go for a minute, okay, right after I spray it, 10 seconds, 15, 20 seconds later, you know what happens. Okay, instead of those particles being right there by the entrance of the can, now they've started to spread out throughout the room. They're going up, they're going down, they're going over. They are becoming more randomly distributed as they move throughout the room. That's an example of entropy. Now, the crazy thing is, this increase in entropy ends up leading to a uniform solution. So we start nice and neat and organized. That's a very low entropy. But things becoming more random, like these particles right here, is actually what leads us to them uniformly mixed throughout the room. I don't know if I can draw this, but I'll try. So think about it this way. If this is your bedroom, okay, and we're looking from your ceiling down onto your bedroom, just go with it, humor me. Here's your bed. We'll give you a big old comfy bed. There's your pillows. Okay, you got a little nightstand right here. You got your dresser. There's your TV and your Xbox. And then just for kicks, there's a chair. You know, we got to give you a comfy room. So you walk in your room every day. Here's you, which is not a top view. Humor me again. So you walk in your room every day and you're getting ready to change clothes. And you take your shirt or whatever it is you're wearing and you throw it over here on the chair. So there's a shirt. Then the next day you walk in and you throw your shirt over here in the corner. And the next day you walk in, you throw it over here on the dresser. And the next day you walk in, I change the color, you throw it over here. And then one goes on the floor. And then one goes on your nightstand. And you keep throwing clothes all over your room. Okay? That is a natural tendency to increase the randomness. Most of you guys probably will do this, and you're not throwing all of your clothes in a nice, neat little hamper, which would be really, really nice. Your mother would appreciate it, but you're probably not. So you are seeing in this an increase in entropy. The clothes are all over the room. But let's say you have enough clothes where you can do this for 365 days. Dude, if you have that many clothes, get them made. But if you had that many clothes and you can do this for that long, you would start throwing one here, and then one here. And then the next day, there would be one over here, and then one over here, and then here, and then here. And you would continue to throw these clothes all over your room. And what would end up happening, sorry, I keep hitting the wrong button. What would end up happening is after your 365 days of throwing your clothes everywhere, all of a sudden, look what I've got. I have a uniform solution. I have my entire room covered in clothes, and even though it started by just randomly throwing my shirt wherever I want, that randomness leads to uniformity within a given space. So, where this leads us to chemistry is we have reactions that are called spontaneous reactions. You've heard the word spontaneous in English, okay? It means just kind of all of a sudden, no planning. So if you remember that things tend towards an increase in entropy, reactions that are spontaneous, that are just gonna happen without a lot of planning and energy and effort put in, those are gonna be reactions that are exothermic. Because if they're gonna be able to give off heat, that is going to favor your entropy. Okay? Think about this. If I'm releasing energy, that's a lot easier than taking energy in. So that's going to be an increase in randomness. That's going to allow it to be a spontaneous reaction. You also will see spontaneous reactions when you move from solid to gas. And that could be solid to liquid, liquid to gas, because again, that's an increase in entropy. Your molecules of a solid, let me scroll a little bit up, your molecules of a solid, you guys know, are packed pretty tightly together. That's not a lot of randomness in there. Everything is organized. Whereas the gas molecules are just kind of pinging all over the place. So these things that are spontaneous reactions, what you see with all of them is an increase in entropy. Ignore that last green line. That was a mistake. Okay, that's an increase in entropy. So, one of the other things that you'll see on your notes on that slide is something about Gibbs free energy. There are calculations that you can do, if you take a college chemistry class, you will learn how to calculate exactly how much Gibbs free energy is released. But essentially, Gibbs free energy is how much energy is released that you can actually use again. It's sort of like the idea we talked about with the cheeseburger, where you eat the cheeseburger, but because you have to use some energy, you don't get all of it. That's the same idea with this Gibbs free energy. So if you see this term Gibbs free energy or simply free energy, it's simply talking about how much energy can then be used in another process. So we learned the first law of thermodynamics last week when we talked about calorimetry. So now we'll talk about the second law of thermodynamics. Second law of thermodynamics, very simply, is that entropy will not decrease in a system over time. It will always go up. So, really simple. Entropy is always going to increase in a system. The one exception to that is if you change the surroundings. So, we talked about the air freshener. There's another can of it. Okay, obviously when I spray it, it comes out in these straight lines, then it goes crazy. But let's say I created some kind of contraption that was like a collapsible box. Okay, so this red thing is my box. If I spray my air freshener into this box, and then I actually crush the sides of the box to make it smaller. So there's the new sides, and I'm going to erase the old ones, and I'm literally smushing down the area where the air freshener is. That's going to violate the second law of thermodynamics. That is going to force a decrease in entropy. But that's not a natural process. That's me actually doing something to force that down. So all of this leads us, yet another place, to the idea of kinetics. We've talked about that kinetic energy, and kinetic means movement. So kinetics is the study of reaction rates. How quickly does a reaction happen? You can see in your notes, it's pretty easy to measure this. You can see how quick the products are formed. You can see how quickly the reactants disappear. You can look for changes in concentration. But if we have A plus B make an AB, just a good old simple synthesis reaction, reaction rate is how fast is that happening. There are, 4 things in your notes that affect reaction rates. And they're pretty obvious when you look at them. Concentration, pressure, temperature, and surface area. All of those have what we call a direct relationship. which means if any of them go up, the reaction goes faster. Common sense, okay? If the concentration of A and B goes up, that means I have more of it. I can make more. That's a faster reaction. If the pressure goes up, it's going to be forcing these two things together. That's a faster reaction. If the temperature goes up, it's going to give each one of these more energy to combine. The molecules move faster. That's a faster reaction rate. And if the surface area is increased, it's easier for these guys to connect together. That's an increase in reaction rate. So that's all very simple. That does tend to be an SOL question where they give you options, and it's one of the ones you have to check multiple things. They'll say which of the following would cause an increase in reaction rate. You can do that. So as we talk about chemical reactions, we have to talk about when they happen, because it's not as easy as here's a molecule, they are immediately under any circumstances going to combine and form a compound. That doesn't happen. Instead, they, one, have to run into each other. But as you can see in the notes, what normally happens is your molecules will bounce off. If these two guys actually come that close to each other, the more likely scenario is not that they're going to make a compound, but instead, my blue one's going to bounce this way, and my red one's going to bounce this way. They have electron clouds around them, which end up repelling each other. That's those negative charges. However, if the molecules have, number one, a large enough amount of energy, okay, so if they're coming at each other with this like breakneck force, and then two, if they're facing the right direction, okay, so if they're in the right orientation, they can overcome that repulsion and they can react. Okay, but you have to have both of those present. It's not just these two happen to be in the same neighborhood and poof, we get a compound. It's not that easy. So the one other factor that has anything to do with chemical reactions, and this is a factor that can increase the reaction rate, is something you guys learned about in biology. It's something called a catalyst. You guys learned in biology that a catalyst is something that speeds up a reaction, but you didn't learn how it works. So here's the basics, okay? Before we get to catalysts, so we'll erase that word, we have to talk about activation energy. Activation energy, and again, this is on the PowerPoint, is the energy required to start the chemical reaction. Think about this. If this is a hill, and I have a rock up here, and there's Allie, standing behind the rock, and there's John down here at the bottom. If Allie felt like crushing John, she does not have to chase that ball all the way down the hill. All she has to do is give it one little shove, and it will roll on its own. That shove is the activation energy. The way it looks with graphs in chemistry is obviously not with people on a hill and rocks. Instead, when you see a graph of a reaction written in chemistry, you saw these with endo and exothermic reactions, you have the reactants, and then lots of times you see the graph go up and then fall back down. That one, for example, would be an exothermic reaction because I start lower than where I start. But you'll notice what happens here in the middle. Okay, this graph actually goes up before it falls down that hill. That's your activation energy. So when you're looking at this graph, between these 2 points is what we are going to call, sometimes it's abbreviated EA, but it is our activation energy. That's the amount of energy it takes to get everything started before it can whoosh and fall down the hill on its own. Okay, so this is my activation energy. The other part of this graph that we see is called the activated complex. The activated complex is this little bump right here. It's that speed bump right at the top. It's the point at which my reaction can go either way. If I don't get up to the activated complex and I only get up to here, no reaction. I'm not high enough. If I go past it and I'm down here, I'm gone. I'm going all the way down here to the end. But right here, teetering at the top, that's my activated complex. It's the point at which my reaction can go either way. And lots of times in chemistry, like the example you see in your notes, you actually have a middleman. You have two things combined to make one thing, and then that one thing continues on to make something else. In the example in your notes, that H2CO3 would be your activated complex. It is the point at which that reaction could go backwards or it could go forwards. So back to catalysts again. Catalysts, you remember from biology, are things that affect reaction rate by speeding up the reaction. What they do to speed up the reaction is they lower the amount of activation energy. So instead of Allie having to shove the rock, I'm going to give her a go-go gadget arm and she can just whoosh, kind of like give it a little bit of a pull the trigger and the hand shoots out and pushes the rock for her. That's lowering the activation energy. It's not part of the reaction. So if the reaction is A plus B yields AB, okay, and this is like A plus B up here, and this is AB down here, my catalyst is not A or B. My catalyst is not in this reaction. Instead, it's written right over top the arrow. So it could be an element, okay? You might see PT as platinum. It could be light. It could be electricity. But what the catalyst does is it lowers your activation energy. You'll notice I'm starting in the same place. I'm ending in the same place. None of that changes. The only thing that is changing is how far up I'm going. So now, instead of this much activation energy, I'm using this much activation energy. I'm making it easier for the reaction to continue. That's the end of what we're going to learn on Monday. I'll make you another video for what's coming on Tuesday.